Morning, everybody. Welcome to Monday of week 10. We're getting there. We are getting there. We can do it. Hello, Michael Paul. Good morning, Ryan. Hopefully you guys had a slightly more relaxing week last week. Although with your physics exam, well, most of you guys, physics exam on Saturday, maybe not. Maybe it was just redirected attention. Good morning, Danya. I'm missing spring break. Yes, spring break. It would be really nice. It really would. I agree. We're almost there. Mostly. We're 2/3 of the way there. 2/3 of the way there. And were there some issues with the physics exam, AP? Good morning, Schwartzmeyer. Yeah. Home stretch. We've got, this is week 10. So 11, 12, 13, 14. It's about 5 weeks of instruction and 1 week of finals. How many classes do you guys normally take a semester? Do you take 4 classes, 5 classes, 6 classes? How many classes do you guys typically take? Four to 5? 17 credit hours, so I'm assuming there's a lab class in there, or there's a couple 4 credit hours. I think math is 7 classes. Ryan, is that seriously 7 classes this semester? Morning, Squiddy. Like, oh my gosh. How do you keep track of everything? A normal semester is so long. I can't remember if I've said this before, but when I did undergrad, I went to a school that did the quarter system, so we had 10-week quarters. It was 10 weeks, and then 11th week was finals. And 10 weeks was like a perfect amount of time. It was great. When I first did grad school and I had a 16-week semester, it went forever. Forever. 6 classes is still a lot. Especially when they're all like math and science classes. I don't know how many gen eds you guys take a semester. I think there's typically maybe 1, depending on your program, a semester. Junior year, though, is like torture for any engineering program. Hopefully you guys have like 1 gen ed. Oh, it's just that's I used to call my fun pathway. I mean, define fun. Like, fun in the sense that there's not that much work to do, or fun in the sense that you really liked that material. I don't know, I enjoyed my gen eds for the most part. I took history classes. Oh my gosh. That's Greek history was mad cool. Mad, definitely mad. I'm assuming you learned about all of the mythology, which is interesting. I loved my history classes. I took World History 1 and 2. That was interesting. I think my history textbooks are the only textbooks I've actually read cover to cover. Python. Oh, Python, it's programming. It looks different. I'm still learning Python this summer in my own time because it's fun. Ooh, ancient warfare in the Mediterranean. Interesting. It's ridiculous how much history is centered around war. Michael, are you a freshman or sophomore? Humans do like fighting. It's very natural. Just ask my toddler. Freshman. Okay. Okay, that makes sense. Okay, let's go ahead and start. Very interesting discussion. I enjoy discussing things with you guys. So just an announcement, exam grades, they should be up tomorrow. There was a little snafu with who was grading what. So they should be up tomorrow. You'll definitely have them. I'm going through the grades right now, trying to make sure they're complete, because the homework grades aren't always complete, which for homework, I can leave that on you guys to inform me, but for the exam, I want everything to be complete, so they should be released tomorrow. I have some extra grading I need to send out to the TAs and graders to finish up, but they should be up tomorrow. This week, we are continuing our linear algebra. So, in the quizzes, the week whatever quizzes, week B quiz, B quiz. Somebody asked, like, why are we solving a bunch of systems of equations? Why do we even care about all these different methods? And this class is called Engineering Computations. It's focused on how do you compute things. And a lot of your engineering classes, it's really, you can put them in terms of systems of equations. You don't have to. A lot of your undergraduate coursework, you don't have to really think about things as systems of equations. A lot of stuff you do, but you don't necessarily need these methods to do it. But linear algebra is really central. It's really key. It kind of weaves its way behind the scenes for a lot of the stuff that you will have in your curriculum moving forward. So that's why we're focusing on it. We're going to go over lots of different ways to solve some systems of equations, and it's going to feel a little redundant, but we're going to go through how to solve them on paper. I wrote a bunch of different functions in MATLAB, algorithms that solve these processes for us as well, so we're going to go over what does it look like to do it algorithmically, writing a program to do it. So there's lots of different ways I guess there's a couple different ways we'll approach each type of problem. AP MATLAB is not explicitly going to be on the final. A lot of the final it's going to be solving with linear algebra. So make sure you are following along with this stuff. Make sure you're doing the examples, doing the homework. Make sure you're also doing the programming project. So the programming project is worth 15% of your grade. I do have videos out there that I created that go over each part of the project. So make sure if you're stuck, go to those videos, watch those as many times as you need to. I think the longest one is maybe 9 minutes. They're not the most efficient videos, but they're also not very long. So make sure you're going to those videos, looking at some hints, tips, tricks for doing all the different parts of the programming project. So make sure you're doing that. Also come to Friday party office hours for the programming project. We had like 10 people there asking questions. It's as much of a party as you can have in Zoom office hours. But it's always nice and fun to talk to other people. Okay, so this week, or today, I do want to go over some stuff for the homework, and then we will get into our material. A couple notes in terms of the homework. When you're talking about vectors that are perpendicular to each other, so they're orthogonal, a 90-degree angle, you can use your cosine equation. So cos equals u dot v over magnitude of u times the magnitude of v. So if you have this as 90 degrees, that means u dot v is going to be equal to 0. So this is what you can use for this part f here. When it says orthogonal vectors over here in our table of equations, this is essentially just Pythagorean theorem, where here's u, here's v, here's u minus v. So it's just Pythagorean theorem. That's what this equation here is referring to when it comes to orthogonal vectors. For part F here, use your cosine equation. Use your cosine equation where u dot v is going to be equal to 0 in order to make this 90 degrees. For problem 2 here, you can also use a cos d. Otherwise, you can't solve for it. I updated the homework document. I did not put that in here, but I updated the homework document. I just missed that one when I was reviewing the homework. For D here, when it says that determine if vector W is a linear combination of the vectors x and y, set it up like this. A linear combination is just a scalar times a vector plus a scalar times a vector plus a scalar times a vector equals another vector. So you would say C1, a scalar, times vector x plus C2, a scalar, times vector y equals W. So plug in what x is, plug in what y is, plug in what w is. You'll get 4 different equations if you multiply through, and then you can solve for what C1 and C2 are going to be. So I think those are the main things in the homework that I wanted to point out. Hopefully it's relatively straightforward. Hopefully you're okay. So Z is not needed. For Z is not needed for part D. You don't need Z. It just says X and Y. In your video it says for part F, if you get 3 different equations. So part F, sorry, I meant you'll get 1 equation with 3 unknowns. Yeah, so you'll get 1 equation with 3 unknowns, pick a value for x1, pick a value for x2, solve for what x3 would be. Sorry, I meant 1 equation, 3 unknowns. For part P2, part B, which side of the equation do we plug into? Can it be either? So the distance between 2 vectors. So yeah, this is just simplifying this side. So these 2 are equal. It's just this side is just a simplified version of this. So either one, it doesn't matter. They're the same thing. Okay, last question about the homework. Let's get into the material for today. So, the material for today, this week we're essentially we're starting to solve our systems. So the reason why we care about vectors is because you can't type double bar in MATLAB. Double bar in MATLAB is the OR symbol, not norm. In order to do norm, you type the norm function, NORM. So the reason we care about vectors is because we can think about a system of equations in a couple different ways. So here I have the system, and essentially what we're trying to do is we're trying to solve for what our unknowns are. What is x and what is y? Given these 2 constraints. So there's a couple ways we can solve it, and you've been doing this, you've been learning this for a while, since however long ago you took algebra. So we can solve for the system using substitution, where I can take this second equation here and rearrange it and solve for x and say that x equals -1 plus y. Once I have that, I can plug this in to my first equation and say 3 times -1 plus y equals 2 plus 2y equals 12. And then I can solve for that. -3 plus 3y plus 2y equals 12. 5y equals 15. Y equals 3. Once I have y equals 3, I can go ahead and plug that up here and solve for x. X equals -1 plus 3 or 2. So I can use substitution. And you've probably been using substitution for quite a long time now. That's one of the ways we can use in order to solve a system of equations. Another way we can use is called elimination, where what we're going to do is we're going to add our equations together to eliminate a variable, and then use that new system in order to solve for our unknowns. So with elimination, here's my first equation. My first equation was 3x plus 2y equals 12. My second equation was 2x minus 2y equals -2. And I'm going to add these 2 together. So I get 5x plus 0y equals 10. So that easily says that 5x equals 10. So effectively what I'm doing is I am replacing one of my equations by adding them together so that my new set is this 5x equals 10, and then I can really pick whichever one I want. 3x plus 2y equals 12. So now's my new set of my new system. This was my original system. So I've replaced equation 2 by adding my equations together, and now I can solve for my unknowns. This equation clearly tells me that x equals 2. And if I plug that in to this one, y would equal 3. So that's elimination. And you've probably, hopefully, you know that should be review. We can also do this graphically. So you can't think of all vectors in terms of dimensions. It's easy to think about vectors graphically when we're talking about 2 dimensions or 3 dimensions. If you have vectors with like 5 values, it's technically still a 5-dimensional space. It's just harder to visualize. In a 2-dimensional space, it's pretty easy. So we can think about these equations as lines. So graphically, we can think about these equations as lines. So if I graph these, it would look something like this. You do not need to have graph paper to do your homework. I will do the examples on lined paper like this because I can easily switch back and forth between them. But you can see here in my lecture notes that I don't have lined paper. I'm just doing it on regular computer paper. Just make sure your work is nice and neat. If you're asked to graph something, just make sure it's neat. Okay, so if I plot these 2 lines, this is the first, or one of them. That's not exactly accurate, but this is 2x minus 2y equals -2, where you can solve for y equals mx plus b, plot it. For this one, it looks something like this. So here's my second one. 3x plus 2y equals 12. And this intersection point at 2, 3 is my solution. X is 2, y is 3. So we can think about our equations as lines, and you've seen that before as well. So should be another review. So we can see it as lines. We can also view a system of equations as a linear combination, or as a bunch of vectors. So if we think about my original system, where I have 3x plus 2y equals 12, and 2x minus 2y equals -2, I can rewrite this as a linear combination, where I have the values in front of my x's, so 3, 2, x, plus the values in front of y, 2, -2, equals my right-hand side, or my b values that we've already seen. So here I can view the system as a linear combination, where here are the values, the vector of values in front of x, the vector of values in front of y, or in front of my first unknown and second unknown, and then my constants on my right-hand side. So I'll call this one vector v1, this v2, this my b vector. And if I plot this graphically, if I look at it graphically, it would look something like this. Okay, so v1 is 3, 2. So here's my x-axis, y-axis, 3, 2. So here's v1. v2 is 2, -2, so 2, -2. So here's v2. And then my b vector. My b vector is 12, -2, so it goes all the way out here. So if I draw that, it would look something like that. We'll just pretend that's good. So here's my b vector. So when we view things as vectors, as a linear combination, essentially what we are trying to do is figure out how much we're going to scale v1. So v1 is on this line. I'm either going to multiply it by a value greater than 1 and make it longer, or a negative number and make it go the other way. But I'm trying to figure out how much do I need to multiply v1 by? How much do I need to multiply v2 by? To the point where I add those together, I end up here with b. So let me erase all my extraneous vectors. So we already know that my solution is 2, 3. So essentially what I'm doing is I'm multiplying v1 by 2, which would get me out to here. So here's 2v1. And then I'm multiplying v2 by 3. So here's 2v2, here's 3v2. So if you're asked to do it graphically, you'll be asked to graph it one specific way. So you'll be asked to graph it as lines or as vectors. So now you can see that if I take this and I add it to this one, I'm going to end up here. So I can create my parallelogram. So that b equals 2v1 plus 3v2. So this is our linear combination. So there's multiple ways we can view a system of equations and solve. We can solve for things using substitution. We can solve for things using elimination. Graphically, we can view equations as lines, which technically are also vectors, where this first line is vector 3 to 12. This second line is to -2 to -2. So we have our vectors as rows, or we can view it as a linear combination, where we have our vectors in front of x, our vector values in front of x, our vector values in front of y, and then our b values. So there's lots of ways that we can view a system of equations. And we already know we can also view it in the form of ax equals b, in matrix form, where a is 3 to -2. Equation 1, equation 2, first unknown, second unknown, x, y, 12, -2. So there's lots of ways that we can view systems equations. Each one's going to give us a set of information. For linear algebra, we're really going to view it in terms of ax equals b. But when you think about it, ax equals b is just where I have column vectors plotted here. Row vectors would be plotted with our lines. So we can view things as just vectors. That's why we're going through all of this fun linear algebra stuff. Okay, so for this material this week, we're really going to focus on something called Gauss elimination with back substitution, which is really just elimination. If I go back to this elimination step here, this elimination, the way I solved it, if I do this in matrix form, let me show you what it looks like. In matrix form, 3 to -2. B 12 -2. This is what my system equation looks like in the form of ax equals b. It turns out it doesn't matter what our unknowns are called. We really don't care about those. It's just unknown 1 and unknown 2. It could be xy, it could be x1, y1, it could be ab. It doesn't matter. So typically what we do is we write what's called our augmented matrix, where we're going to put our a and b values together. So here's the values of A, and then here's B, and we just draw a line between them to distinguish between the two. So you should be comfortable with all of these different ways to write a system of equations. Writing the system explicitly out like this, writing it in ax equals b, or writing it what's called our augmented matrix. Okay, so this system is the same as this. This one on top here just has my letters and my equal sign. This one on the bottom here is just my coefficients and my constants. So in order to do this elimination step up here, I essentially took equation 2 and replaced it by adding equation 1 and equation 2. If I did that same thing here, it would look like this. 2 plus 3, which was 5, negative 2 plus 2, which was 0, and then negative 2 plus 12, which was 10. Where I took row 2, or equation 2, and I replaced it by saying row 2 plus row 1, or equation 2 plus equation 1. But this system here is the same as this system here. If I rewrote my system of equations, it's going to be 5x plus 0y equals 10. This one is 3x plus 2y equals 12. And based on that, I can easily solve my unknowns again. This tells me that x equals 2. And if I plug that in, it tells me y equals 3. So this week, this set of material, we are essentially going to be doing this elimination in matrix form, rather than doing it with our system explicitly with all of our unknowns typed in, all of our unknowns written in. Okay, so let's go through an example of Gauss elimination with back substitution. Before we get to that, I just want you guys to know, so there's some vocabulary in your homework for this week called the trivial solution or non-trivial solution. And I forgot to put it in the notes this week. It's in the notes later on in the semester. It's just not in this week. But a trivial solution is one where all of our unknowns are 0. Where x equals 0, y equals 0, z equals 0, x1 equals 0, x2 equals 0, x3 equals 0, whatever your unknowns are called, they are all equal to 0. It's trivial because 0 plus 0 plus 0 plus 0 equals 0. The non-trivial solution is one where all of our unknowns are, or not all of our unknowns are 0, where we might have x equals 0, but y equals 1, and z equals 3. So it's the fact where not all of our unknowns are 0. So a trivial solution, all of our unknowns are 0. Non-trivial, they're not all 0. Just some vocabulary for your homework. Okay, so let's say we have to solve this system of equations. When we're using Gauss elimination with back substitution, first we are going to write what's called our augmented matrix. So you can write it in the form of ax equals b. A looks like this: 3, 5, negative 2, 4, 1, 1, negative 4, 5. My unknowns are x, y, z, and my b values are negative 15, 21, 21. My augmented matrix, I'm just going to put A and B next to each other. Just squish them together. Put a line in between. 3, 5, negative 2, 4, 1, 1, negative 4, 5. Negative 15, 21, 21. So here's AX equals B. Here's my augmented matrix. That's step 1. Write my augmented matrix. And you will do this forever. It will be so second nature to you. Given a system of equations, write it in matrix form. Write your augmented matrix. Now we want to do our elimination. We want to go through and we want to end up with a situation where one of our equations has one unknown, one of our equations has 2 unknowns, and one of our equations has 3 unknowns. So what we're going to do is we're going to do what's called row operations on this matrix so that we're going to end up with what's called a lower triangle of zeros. I want to put a 0 here, a 0 here, and a 0 here. That is my goal. Because if I have a 0 here, if I have zeros here, that means I'm going to have an equation with 1 unknown. If I have a 0 here, then I have an equation with 2 unknowns, and then my first one would have 3 unknowns. So that is my goal. With Gauss elimination with back substitution, my goal is to get a 0 here, here, and here. There are multiple ways you can do this. Some of you guys may have actually done this before in high school. Some of you guys may have not. But there are multiple ways you can do this. And as long as you do your math correct, you should get the same answer. AP, that's a really good question. No. And I'll mention what this is, but we need to get a lower triangle here. This is where our lower triangle needs to be. These ones need to be zeros. in order for it to be traditional Gauss elimination with back substitution. Technically, you can put your lower triangle on the right and also solve your system. But in order to officially do Gauss elimination with back substitution, we need to have the triangle be over here. So like I said, there's multiple ways to do this. We just want to do our row operations. So we can multiply a row by a constant. We can exchange rows, and there's a reason why we might do that. We'll go through some more examples. And then we can also perform our elimination step, where we're going to replace a row or an equation by adding it to another equation. Okay, so I'm going to go through these steps algorithmically. So I'm going to go through the steps that always are going to apply in, or most always going to apply in a given scenario. So I'm first going to make this a 0. I'm going to start there. And I'm going to use this number to do it. So the first thing I need to do is I need to make sure that when I add this equation and this equation, or that row 1 and row 2 together, these two numbers here are going to be equal but opposite, or they're going to be equal. So first I'm going to take row 1, and I'm going to multiply it by 4, and I'm going to take row 2, and I'm going to multiply it by 3. So when I do that, I'm going to wrote out my work, so hopefully I don't make math errors. Still made a math error this morning, but that's okay. Row 1 becomes 3. I should erase things so I don't get my minus signs messed up. 3, 4. 3 times 4 is 12. 4 times 5 is 20. 4 times negative 2 is negative 8. And then 4 times negative 15 is negative 60. For row 2, 3 times 4 is 12, 3 times 1 is 3, 3 times 1 is 3, 3 times 21 is 63, and then row 3 doesn't change. So negative 4, 5, and 21. So now I'm going to make this a 0 by saying that row 2 equals row 2 minus row 1. And I'm showing out all of my steps explicitly. As you do these row operations a lot more, you'll get a little bit more comfortable with combining steps, but I'm just going to be explicit about everything I'm doing right now. So row 1 isn't changing. I'm using row 1, but I'm not changing it. I'm not replacing it. So row 1 doesn't change. Row 3 doesn't change either. Row 2 now is going to be 12 minus 12, which is 0. 3 minus 20, which is negative 17. 3 minus negative 8, which is 11. And then 63 minus negative 60, which is 123. So I have a 0 here. That is the first step. That's always the first step that you can use. You don't have to, but algorithmically, if we're always going to apply the same steps, you start by making this one a 0. You can always use this number and that number. You just have to multiply them, figure out what you need to multiply in order that they're equal, and then opposite. My next step, I want to make this negative 4 a 0. And I'm going to do that using this 12. So in order to make sure that they're equal, I need to say that row 3 equals row 3 times 3. So row 1's not changing. Row 2 doesn't change. And now row 3 is going to be multiplied by 3. So negative 4 times negative 4 times 3 is negative 12. Negative 4 times 3 is negative 12. 15 times 3 is 15. 21 times 3 is 63. Now I can add my rows together to get a 0 there. So row 3 is going to be replaced by row 3 plus row 1. Row 1 doesn't change. I'm using row 1, but it doesn't change. 12, 20, negative 8, negative 60. Row 2 doesn't change. Row 3 is going to be replaced by saying negative 12 plus 12, which is 0. Negative 12 plus 20, which is 8. 15 plus negative 8 is 7. 63 minus 60, or plus negative 60 is 3. So now I have a 0 here, like I wanted. Okay? So start by putting a 0 here, then put a 0 here. You do not have to do it in this order, but this is the order that you can always apply in every scenario. Now, lastly, I want to make this a 0, and that's going to give me my final lower triangle. So to do that, I'm going to use this number. So first I need to take row 2 and I need to multiply it by 8 and take row 3 and multiply it by 17. Remember, I want these two numbers to be the same with opposite signs or not opposite signs. It just depends on whether or not I'm going to add my rows together or subtract them together. So row 1 doesn't change. Row 2 is now going to be 8 times 0, which is 0. 8 times negative 17, which is negative 136. 8 times 11, which is 88. And 8 times 123, 984. I like to use whole numbers. If you use whole numbers, you're going to end up with large numbers. And that's fine. It doesn't matter. They'll divide out most likely in the end. You can deal with fractions. It's up to you. There are multiple ways to go about these row operations. As long as you do your math correctly and you follow the rules, we should all end up at the same answer. Starting from A, we all start out at A. At the top, we all start out with this. Same augmented matrix. We should all end up with the same answer, but how we get there is going to be different depending on your preference, depending on what you choose to do. Okay, for row 3, I get 17 times 0, which is 0. 17 times 8, 136. 17 times 7, which is 119. And 17 times 3, which is 51. Now I can say that row 3 is going to be row 3 plus row 2 to make this a 0. So row 1 doesn't change. Row 2 doesn't change. I'm using row 2, but it doesn't change. And then row 3 is going to be 0 plus 0, which is 0. 136 plus negative 136, which is 0. 119 plus 88, which is 207. And then 51 plus 984, which is 1035. Once again, you get large numbers, but they should divide out. So this here is my final result. I have my lower triangle of zeros. If I write my system, this is going to have just z in it. This is going to have z and y, and this is going to have x, y, and z. I can also clean up this final matrix and do some division before I write my system equation. So I could say that R1 equals R1 divided by 4, R2 equals R2 divided by 8, and R3 equals R3 divided by 207. If I do that, I end up with 3, 5, negative 2, negative 15, 0, negative 17, 11, 123, and then 0, 0, 1, and 5. So these are smaller numbers to deal with. But note, these two are exactly the same. One's just scaled. So writing my system of equations, I can see here that z equals 5. Woohoo! That was nice and easy. Plug that into this one. Negative 17y plus 11z equals 123. I plug it in, and I can say that y equals negative 4. And then this one here says that 3x plus 5y minus 2z equals negative 15. If I plug in my z and y values, it should tell me that x equals 5. So we can, technically, treat the system of equations, do substitution, and it will work. Or we can do Gauss elimination and treat it as a matrix and do row operations on our matrix, where we can multiply a row by a constant. We can replace a row by adding it to another row. And we can also exchange rows as well, which there are reasons why you might want to do that. End up with our lower triangle of zeros so that we have an equation with one unknown, an equation with two unknowns, an equation with three unknowns, and we can easily solve. This final matrix we end up with is called REF, reduced echelon form. In reduced echelon form, we get a staircase of zeros. We get that lower triangle, where these first non-zero digits in a row, these are called our pivot locations. And they form in this staircase pattern. Yeah, so this is REF. If you are asked to find REF, reduced echelon form, this is where you get your lower triangle of zeros. So we can always go in this order. We can always find this zero first, find this zero, and find this zero. If you want to do the same steps every time, you do this. You don't have to do that though. You're not constrained by doing this algorithmically. It's nice to do it algorithmically because you don't really need to think much about your steps, but we can do our row operations any way we want. So given this augmented matrix here, I just know I want to end up with a zero here, here, and here. So my first step could say that, okay, I know this -4 and 4 are the same, so I could just say that row 2 equals row 2 plus row 3. It's row echelon form. Let me, I think I said it correctly this morning. Yeah, right, row echelon form, not reduced row echelon form. Sorry, thanks, AP. Row echelon form. REF is row echelon form. So the single R, one R. The double R is reduced row echelon form. Thank you. So I could say initially that R2 is going to be R2 plus R3. Where row 1 doesn't change. And row 2 is now going to be 4 plus -4, 0. 1 plus -4, which is -3. 1 plus 5, which is 6. And then 21 plus 21 is 42. And then row 3 doesn't change. So it's -4, -4, 5, 21. So I could start out there and just say, I don't want to deal with using this 3 right away. And I just want to say that row 2 is now going to be row 2 plus row 3. Because my 4 can cancel out my -4. And I got my first 0. That's great. And then I can continue. I can get this one. In order to make this a 0, you have two options. You can either use this number here, the 0, or the 3. In reality, though, you can't use a 0 to make another number a 0 because 0 is never going to cancel out a non-zero number. So I need to use this 3 here. But that's fine. I could just say row 3 equals 3 times row 3 plus 4 times row 1. So now I'm combining my row operations together. Rather than doing my multiplication step on each row individually, I just combine it into one row operation. Where I'm saying row 3 is just going to be 3 times row 3 plus 4 times row 1. Note, when you do it this way over here where you separate them out, it's much easier to follow your work. If you are combining row operations, which as you get more comfortable, you will do it, and there's just less steps then, less to write, I encourage you to show a little bit more of your work. So for this row operation, row 1 isn't changing. Let me space it out a little bit more. Row 2 isn't changing. And now 3 is going to be 3 times -4, or -12, plus 4 times row 1, or 4 times 3. So -12 plus 12. Then I have 3 times -4, plus 4 times 5. 3 times 5 plus 4 times -2, and then 3 times 21 plus 4 times -15. So notice there's more to keep track of. There's more room for error. So you're going to do more writing to show your work. So when I do this calculation, I get 3, 5, negative 2, negative 15, 0, negative 3, 6, 42. 12 minus 12 is 0. Negative 12 plus 20 is 8. Negative 15 plus negative 8 is 7. 63 plus 6, negative 60 is 3. So I've got my zeros here, and now I can get a 0 here. So I can say that row 3 is going to be 8 times row 2. I have to use this number here because I want to keep my 0 here. You will get more comfortable with knowing what to do as you do problems, as you practice. So 8 times row 2 plus 3 times row 3. So you could also show your work like this. Just say row 1 doesn't change, row 2 doesn't change. And then just show your work for row 3, where you're saying 8 times 0 plus 3 times 0, 0 plus 0. 8 times row 2, or 8 times negative 3, negative 24 plus 24. 8 times 6, which is 48, plus, I should look at my work, plus 3 times 27, or 5 times 7 is 21. And then 8 times 42, which is a larger number, 336, plus 3 times 3, which is 9. So this is acceptable for showing your work as well. And then just write your final answer. These problems take a while. They take a while because there's so many steps. There's so many numbers to write. I like to say that linear algebra is just addition and multiplication, but there's a lot of it. You can miss one simple sign and it can just mess your problems up. So it's really important that you show your work, that you're being careful with everything that you're doing. So 0 plus 0 is 0. I made a mistake this morning and I found my error right away, but a lot of times you don't find your errors right away. A lot of times it's literally just one little small sign. Do you always keep the higher row when adding, subtracting between rows? So the way that I do most problems is using this algorithm form, this algorithmic step, where I'll mention that in a minute. Let me finish this problem. So negative 24 plus 24 is 0. 48 plus 21 is 69. 336 plus 9 is 345. So now I can solve. 69z equals 345. This ends up being z equals 5. Then I have negative 3y plus 6z equals 42. If I plug in z equals 5, this gives me y equals negative 4. And then this one, 3x plus 5y minus 2z equals negative 15. If I plug in my y and z values, I end up with, x equals 5. So my answer is still the same. My answer that I end up with here matched exactly what I got down here. We just did different row operations to get from my augmented matrix to my answer. So notice this also is REF. I have my lower triangle of zeros. So there are multiple versions of REF you can get from an augmented matrix. It just depends on your row operations, which you are free to use any row operations you want. You just want to end up with that lower triangle of zeros. So AP, what you mentioned is, so my algorithmic steps, if you look at an augmented matrix, so let me just copy and paste this down. 3, 4, negative 4, 5, 1, negative 4, negative 2, 1, 5, negative 15, 21, 21. If I look at this augmented matrix, I know I need to get a 0 here, a 0 here, and a 0 here. Most of the time, you can do that in 3 row operations. You can use a row operation to get this one, a row operation to get this one, and a row operation to get this one. To get your zeros in column 1, you can always use this first number. unless it's a 0. If it's a 0, you're going to need to swap rows. But for the most part, yes. So Benny, that's a good question. You can only multiply a row by a scalar, a non-zero scalar, really. You don't want to multiply a row by 0 because you're losing all the information. But you cannot multiply a row by another row. You can only add or subtract rows together. So I can always use this number here to put zeros below, where essentially I can say that row 2 is going to be some multiple of row 2 plus some multiple of row 1. It just depends on what these m and n values are. You can deal with fractions, that's completely fine. I like whole numbers. So I typically say, okay, for this example, it would be, I need to multiply row 3 or row 2 by 3 and row 1 by -4. Same thing for row 3. I can replace row 3 by saying some multiple of row 3 plus some multiple of row 1. For this example, it's going to be 3 row 3 plus 4 row 1. And then my last row operation I can use to get this 0. And I can always use whatever number ends up being here to do that. Where I can say row 3 is going to be some multiple of row 3 plus some multiple of row 2. So I can always use these 3 row operations to get REF for a 3 by 3 matrix, for a 3 by 3 system. So in general, AP, I'm always replacing the lower one because I'm always using a higher row to do the elimination step. You do not have to. For this first step here, we replaced row 2 by adding it to row 3. So it's really just a preference. It's really up to you as long as it's valid. You have a lot of freedom to do whatever row operations you want. Some are going to be easier than others. Notice when you put a 0 in a location, when you put a 0, like when you have a 0 here and a 0 here, and you're trying to find a 0 here, you want to make sure that the 0 doesn't go away. So you'll get experience. Sometimes you might go in circles, but you'll get experience when doing problems on which rows you can really use to eliminate values in other rows. Okay, so like I said, when it comes to an algorithm, you can always use these 3 steps. If you're doing it with fractions, you can do it with fractions as well. Your row operations look the same. It's just row 2 is going to be replaced with row 2 plus some now fraction with row 1. In this instance, I would multiply it by 4/3 and subtract it. So there's lots of ways you can do things. This is if you want to deal with fractions. This is if you want to deal with whole numbers. If we looked at it in MATLAB, like I said, I wrote nice little algorithms in order to do this. It made me happy. One Friday. So if you look at it in MATLAB, I wrote a function. First of all, I wrote a function that does row operations. So here's a function. It's called RO. It does a bunch of row operations. It takes in your A matrix. So in this instance, an augmented matrix. What type of row operation? So if it's row operation 1, you swap 2 rows. If it's row operation 2, you multiply a row by constant. If it's row operation 3, you perform your elimination. So that's this function. And then my Gauss elimination function looks like this. It essentially goes through those steps that I just mentioned. Starting with row 1, it's going to create zeros in row 1 in column 1. It's going to create zeros in column 1 using my row 1 value, using my pivot location in column 1, that top number. And then it's going to put the row or the zeros in column 2 using my 2 location, that second location. And it's going to put zeros in row 3 if it's bigger, or in column 3 if it's bigger than a 3 by 3. So that's what this does. So for all of my pivots, those values along the diagonal, this checks to see if that pivot is a 0. If that pivot is a 0, then you need to swap rows So it just swaps it with a non-zero value in a row. And then here's where it performs its elimination step. So here's that multiplier. Essentially, I'm dealing with fractions because it's in MATLAB. I can deal with fractions. It's easier to deal with fractions in MATLAB. And then I'm doing that elimination step. I'm replacing a row R, by adding it to some multiple of my pivot row. And then here's where I perform back substitution. So as a human, we can kind of look at a problem and we can pick and choose which row operations we want to use. In MATLAB, if we're writing a program that does it, we can figure out what this looks like algorithmically. So I can solve this. Let's see, my original matrix, so A, B, my augmented matrix looked like this. 3, 5, -2, -15, 4, 1, 1, 21, -4, -4, 5, 21. And then I can just call, let me show what's actually happening. So x equals Gauss elimination, AB. So we can see how this algorithm did my, it's not the correct solution though, which is weird. I can deal with that later. But my zeros are correct. And it dealt with fractions. So it first took this row and made a zero here by saying negative, oh, thank you. -2. Oh, come on. Now I can call. Thank you. There we go. So here's my original matrix. It made this a 0 by taking this row and adding it to 4/3 my first row. Then it made this a 0 by taking this row and adding it to 4/3 of my first row. It dealt with fractions because it's MATLAB. It can deal with fractions. It's easy. I like whole numbers on paper because my brain is easier. It's easier to think for me in whole numbers. And then it made this a 0. And then it performed back substitution. So the back substitution algorithm takes a little bit more thinking. It involves dot products. But in my brain, I had to sit there and be like, okay, how do you do this algorithmically? Like, I know how to do it on paper. On paper, it's really easy, but how do you program it in? So I'm not going to go through that. But we can see all of the steps, and we can see what the solution is. Notice this also is REF. It's a different REF. Gets the same answer, but different REF. Okay, so that's gonna go. We're gonna stop there today because we're running out of time. I will go over more examples on Wednesday. We're gonna do Gauss-Jordan elimination, which is essentially the same thing, just more row operations, and then also finding the inverse. Okay, but we're gonna stop there, and yeah, we'll stop there. So with that, welcome back to this class. It was a little bit more of an adjustment. Opening Twitch this morning, remembering to click all the right buttons. And I'll see you guys on Wednesday. Any final questions? Okay. See you guys on Wednesday. Don't forget to look at the programming project videos. I hope they're helpful. So for homework part 1, problem F. So write out your dot product, given arbitrary values of x1. Pick values for x1, x2, and then you can solve for what x3 would be. Okay. See you guys later.